for me.
I mean, I'm pretty chill. Like, you give me the right answer, like I'm happy, you know? So, no pressure, but I'm happy. Yeah. Mhm. But it's not bad though.
I think that's the other thing, the HK, I can show with that. You know how many questions is gonna be on that?
Like one. Yeah.
All
Yeah.
questions are extremely long.
Um, some of them. I mean, some of it is like the last test. Like some of them were like yes or no questions. You know?
Were they allowed to get some question on the last one?
Yeah. Yeah.
How many words?
Yeah. All right, let's jump into this real quick, right? So suppose that we know that the cost of making a product is dependent on the number of items X produced, right? This is given by the equation C of X cost is equal to 15,000 X minus 0.1 X squared plus 1,000. If we want to know, let me just make sure something good, okay? If we want to know the average cost of producing X items, we should divide the cost function by the number of items X, right? So the average cost function, which yields the average cost per item for X items produced, is f of X is equal to 15,000 X minus 0.1 X squared plus 1,000 divided by X. Okay. Many other application problems require finding an average value in a similar way, giving us variables in the denominator. Written without a variable in the denominator, this function will contain a negative integer power, right? So in the last few sections, we worked with polynomial functions, right? Or which are functions with non-negative integers for exponents. In this section, we're going to work with rational functions, which have variables in the denominator, right? Not bad. We kind of spoke about this before, but now we're like kind of diving into it a little bit, you know? It's not too bad. So now we're gonna talk about using arrow notation. So we have seen the graphs of basic reciprocal functions and the square reciprocal function from our study of the toolkit functions, right? Let's examine these graphs and then we'll talk about them, right? So on the left, right, we have the graph f of x is equal to 1 over x, right? So notice how it goes from negative infinity and then it just drops down by the y axis, and then it comes back up from positive infinity and drops down to negative infinity, and it doesn't cross the x-axis. This is 1 over x, right? Then we have the inverse, right, of the reciprocal, right? So that's 1 over x squared, right? So notice how that one goes up to the y-axis, but it doesn't cross the y-axis, right? And it's also it's going up, right? So all the y values are positive, right? That's another observation we can make about that. Okay. It's gonna be fun. All right. So several things are apparent if we examine the graph of f of x equals 1 over x. So that's this first one right here. All right. So on the left branch, right, of the graph, the curve approaches the x-axis, which is y equals 0, right? As x goes to negative infinity, right? Negative infinity is like all the way to the left, right? As the graph approaches 0, right, from the left, right, the curve drops, right? So as it's coming to 0, the curve is dropping down, right? From the right. The curve rises, right? Finally, on the right branch of the graph, the curve approaches the x-axis y equals 0 as x goes to infinity. So to summarize this, we use the arrow notation. So this is arrow notation right here, right? So let's say that we have x is approaching some number, I'm just using a for example, from the left, right? That little negative sign there means it's approaching from the left. Wait, this is left. Sorry. Right? And then you have x is approaching some number, let's call it a, with the little plus sign. That means it's approaching from the right. So this is from the right. Left is this way, right that way, right? You have x is going to infinity, right? So that's x approaches infinity, or x will increase without bound, right? Then we have x is approaching negative infinity. That means that x is approaching negative infinity is going without bound to the left, right? F of x goes to infinity, right? We're going all the way up, right? The output approaches in infinity, the output increases without bound. F of x approaches negative infinity, right? So that means that we're going to the left, negative, oh no, down actually, excuse me. All right, f of x approaches negative infinity, the output decreases without bound. And f of x approaches a, so the output is approaching a particular number. All right. Some of this might be like over your head. That's okay. You'll see this again in calculus. All right. When you see limits, yay. Fun stuff. All right, let's talk about the local behavior of f of x equals 1 over x. So let's begin by looking at the reciprocal function. F of x equals 1 over x. We cannot divide by 0, which means that the function is undefined at x equals 0, right? So 0 is not in the domain, right? As the input values approach 0 from the left side, becoming very small negative values, the function values decrease without bound. In other words, they approach negative infinity, right? As you can see here, right, in this table. So we have these x's, they're getting smaller, right? This is like 10 cents. This is a penny. This is smaller than a penny. This is even smaller than a penny, you know? But you see the values right here, right? This is going from negative 10 to negative 100 to negative 1,000 to negative 10,000, right? It's just flying away, going to negative infinity, right? And we write in arrow notation as x approaches 0 from the left, right? F of x is going to negative infinity, right? So that's how you would say it in arrow notation.
So it's kind of like, zero kind of negative infinity, going for zero to negative infinity, or
It is, yeah. This is like another way of saying that.
do you have to do that?
Suggested. You can write it in words. I'm not opposed to y'all writing in words. Y'all could describe things if y'all want. Y'all don't have to use the math notation. You know? So as the input values approach 0 from the right-hand side, becoming very small, positive values, right? The function values increase without bound, approaching infinity, right? So as we can see, so we have 10 cents, and we have like a penny, and we have a fraction of a penny, we have an even smaller fraction of a penny, right? And you see how it's going from like 10 to 100 to 1,000 to 10,000, right? It's just going off straight to infinity, right? So we can write that in arrow notation as x is approaching 0 from the right, right? F of x is going to infinity, all right? So that's how that's described. Just to show you guys what I'm talking about, you can kind of visually see it here. I'm gonna make this too small, too big, right? So here's our graph, 1 over x, all right? So as x is approaching infinity, right? You see f of x is going to 0, but as this is approaching infinity from the right. Let's say that as the function f of x, right, is approaching 0, right? 0 is the y-axis, right? As it's approaching 0, it goes straight up to infinity, right? And then the reverse is true as well. as x is approaching negative infinity, right? F of x is going to 0. So it's never going to actually get to 0, but it's going to get really, really close. And then opposite is true as the function is approaching 0 from the left, right? So 0 from the left-hand side right here is going to negative infinity. All right. Just a little description. So now I want to talk about something that I kind of just like breezed over for a second, right? So this behavior, right, at y equals something at y equals 0 creates a vertical asymptote, which is a vertical line that the graph approaches but never crosses, right? In this case, the graph is approaching the vertical line x equals 0. So as the input becomes close to 0, this is what happens, right? It's going to get close to 0, but it's never going to actually cross it, right? And we all know it can't cross it because at 0, that is actually undefined, right? We remember that. So real quick, let me hit y'all with a definition. So vertical asymptote, right? A vertical asymptote of a graph is a vertical line, x equals a, some random number, where the graph tends towards positive or negative infinity as the input approaches a from either the left or the right. And you can write this as x is approaching a from the left, f of x is going to approach positive or negative infinity, or you could say as x is approaching a from the right, f of x is approaching positive or negative infinity, right? Just telling you how to state the answer. Let's talk about the end behavior. This is a little bit different, right? Because we have 1 over x here, right? So end behavior of f of x is equal to 1 over x. As the values of x approaches infinity, the function values approach 0. As the values of x approaches negative infinity, the function values approach 0. So here's how it looks on the graph, right? So as x is going to infinity, right? As x is going to infinity, f of x is going to 0. And as f of x is going to negative infinity, f of x is going to 0, right? So it's going to get really, really close to that line y equals 0, which is the x-axis, but it's never going to cross it. All right? Never going to cross it. This is dope. All right, let's add more fuel to the fire real quick. Here we go. So based on this overall behavior in the graph, we see that the function approaches 0, but never actually reaches 0, right? It seems to level off as the input becomes large. This behavior creates an horizontal asymptote, right? Horizontal asymptote. So a horizontal line or horizontal asymptote, excuse me, is a horizontal line that the graph approaches as the input increases or decreases without bound. In this case, the graph is approaching the horizontal line y equals 0. All right. And you guys can see that, right? As it's going, it goes all the way to y equals 0, but it does not cross y equals 0. I'm just going to hit y'all with a definition real quick. So horizontal asymptote. So a horizontal asymptote of a graph is a horizontal line, y equals b, where the graph approaches the line as the input increases or decreases without bound. So we write as x is approaching infinity or x is approaching negative infinity, f of x is approaching b, all right? B is some random number, all right? Let's try this out. So we're going to use arrow notation, right? We want to describe the end behavior and the local behavior of this graph, all right? So here's our graph right here, right? Tell me about it. What is going to negative infinity? The blue lines is what I need you to tell me about. The blue lines. The dotted lines are asymptotes, right? So you could tell me about that too, right? The asymptote is what the blue lines are going towards, right? So looking for something a little more detailed, all right? All right, so look. We'll do this in pieces, all right? Trying to think of a color. All right. So let's start off with the horizontal asymptote, right? So as x is going to infinity, right? What is it approaching? So this is the horizontal. However you spell that word, right? So it's approaching what? Y equals 4, right? So this is as x goes to positive infinity and as x goes to negative infinity, right? F of x whatever is approaching 4, right? That's simple. Let's say the vertical asymptote now. You know what? Hold on. Let me change colors. Let me change colors. Let's say the vertical asymptote now, right? However you spell that word, right? So as x approaches 2 from the left or from the right, pick one. It doesn't matter. Okay, so as x is approaching 2 from the left, right? Where is it going? F of x is going to what? Perfect. Right? It's going to negative infinity, right? So I'm talking about from right here, right? This is the left-hand side. It's approaching 2 from the left, right? As I should say right? And as x is approaching 2 from the right, right? So I'm talking about up here now, right? F of x is approaching, what is it? Infinity. That's it. Okay. So basically, I'm just asking you to describe what's happening. You know? Now, it is. Yeah. Now, yeah. Mhm. So I'm being lazy using like math knowledge and stuff here, language, right? You guys can write it in English if it's easier for you. I'm fine with that. You know, no pressure on that. Huh? True. True. All right. So let's try another one. So it says to use arrow notation to describe the end behavior and local behavior for the reciprocal squared function, right? So that's so we're clear, right? Reciprocal square function is what again? Tell me. F of x equals what? 1 over x squared, right? That's it. All right. And in case we need to remember what that looks like, here we go. That's what it looks like. So talk to me. What's going on? We don't have what? I mean, if you want arrows, here you go. Mhm. No, as x is approaching what? Infinity. Okay, as x is approaching infinity, f of x is approaching. Very good. All right. And as x is approaching negative infinity, f of x is approaching what? Very good. All right. So that is my horizontal asymptote. I can't spell that word. Y'all get the idea. All right. All right. What about my vertical asymptote? All right. So as x approaches what? Okay. Let's do it one at a time. Let's say 0 from the left, right? F of x approaches infinity. Good. And then let's go again. And 1 second. As x approaches 0 from the right, f of x approaches. Perfect. That's it. That's full credit. Negative infinity would be down. Yeah, yeah.
But they don't have next to there.
Right. So they both approaching positive infinity. Yeah. From the left and the right. Yeah. Like literally just describe what you see. That's all it is. Mhm. Not bad, right? There's a couple of questions on this. Do you really need to memorize it though? Do you really need to do that?
It's just nice to have an example.
You have a calculator. What more do you need?
Calculator is gonna give me exactly that.
Type it in. 1 over x squared and see. Yeah. All I'm asking you to do is describe to me in words what's happening. That's all. Mhm. Let's see. Let's talk about this. Go ahead. Go back up.
This will be is example.
Yeah.
These for the bird. That's the X equals to 0.
From the left and the right.
Let's see, X approaching. I mean, it's in the approaching X. The 0 is.
So X equals 0 is a vertical line, right? The y-axis. So as the graph is approaching 0, it goes to infinity. Like that.
Okay.
Yeah. If that sounds confusing, explain it in words your way. I'll take that too. Yeah.
So like also change that it's so
Mhm.
0 and that with y equals infinity.
Right.
There's hanging on like that. But X does something, mathematics, aka the y-axis does this.
Right. That's it. All right, let's look at this. So solving applied problems involving rational functions. Yeah. Another example, we shifted a toolkit function in a way that resulted in the function 3x plus 7 over x plus 2. This is an example of a rational function. A rational function is a function that can be written as the quotient of two polynomial functions, right? Many real-world problems require us to find the ratio of two polynomial functions. Problems involving rates and concentrations often involve rational functions. Right? Let me just hit y'all with a definition real quick. So a rational function is a function that could be written as a quotient of two polynomial functions. All right. So P of X and Q of X, right? So F of X is going to be equal to P of X divided by Q of X. So it's a polynomial divided by a polynomial. That's it. All right. Questions on this? That's all a rational function is. Just want to let y'all know. Give y'all a little analysis real quick, just quick note. So to find a horizontal asymptote, right? Divide the leading coefficient in the numerator by the leading coefficient in the denominator. All right. Giving y'all special. All right. I know y'all miss our old friend domain, so let's go back to domain real quick. I like domain because it rhymes with lo mein. All right. So finding the domains of rational functions, right? A vertical asymptote represents a value at which a rational function is undefined. All right. So that value is not in the domain of the function. All right. A reciprocal function cannot have values in its domain that cause the denominator to be equal to 0. In general, to find the domain of a rational function, we need to determine which inputs would cause the division, right, by 0. All right? Very simple, very simple.
I don't know what we did before.
It's exactly what we did before. Except low-key, I'm just like kind of telling y'all what it is. Those of you that take notes, if y'all write it down, that's half the answers to your homework is right here. All right. So domain of a rational function. The domain of a rational function includes all real numbers except those that cause the denominator to be equal to 0. Period. All right. Probably my favorite definition so far in the class. Just simple, nice, right to the point. That's what it is. All right. Having fun with this one right here. All right. So let me give you all a little bit of tea, a little how to. So given a rational function, right, we want to find the domain, right? This is how you do it step by step. Step one, set the denominator, the bottom of the function, equal to 0. Step two, solve to find the x values that cause the denominator to equal 0, right? And step three, the domain is all of the real numbers except the ones that you found that would make the denominator equal to 0, or in step two. That's simple, all right? Oh, we about to take it up a notch with this one. It's about to get complicated right here. Let's try this out. Let's try this out. So we want to find the domain, my fault, the domain of a rational function, right? Mhm. So here we go. Find the domain of f of x is equal to x plus 3 over x squared minus 9. Oh, shoot. How do I do this? All right, so I'm gonna set the domain equal to 0. So I have x squared minus 9 is equal to 0. All right, let's solve for x. Right, so I'm gonna add 9 over here. What I do to one side, do to the other. X squared is equal to 9 square root this. What I do to one side, do to the other. So x is equal to plus or minus 3. Right, boom. All right, so what's my domain? The domain is, I almost wrote domain right there. Is what? All right, negative infinity
Negative 3.
to negative 3. Okay. Uh-huh.
Negative 3.
Okay.
Positive
3. Uh-huh. Keep going. What else?
3.
Very good. I'm impressed. Well done. Okay. Questions on this? You good? I ran out of space. That's why they're not on the same line, but it should be like, let's see. It should be all together like that, but I ran out of space. That's why it's like that in pink. Just letting y'all know, in case y'all were wondering. All right. So we good?
Just the same thing, you said it equals to 0, square root it.
Yeah. If you didn't want to do that, you could have factored it and set both of the factors. You could just, whatever. I don't care. Yeah, we advanced in here. So whatever y'all do to get the answer, y'all do to get the answer. Okay.
So can I do the homework for that?
Yeah.
Let's do it.
Yeah.
It's up.
Yeah. Everything is posted. Except for the end of what we're doing today. I'm gonna post that like tomorrow or something. Yeah. So real quick, right? This is how the graph would look, in case anybody was wondering, right? So this would be x is equal to positive negative 3, right? So at negative 3, right? This is called a discontinuity right here, right? I'm gonna get into why that happens a little bit later in the lecture, but just know what's happening at negative 3 is that there's no point there. It's an open circle, so it's like it just goes to it and then just like jumps over and then keeps going, right? And then at positive 3, you have your asymptote, right? So I'm gonna tell you guys how to find those two things in a little bit. All right. Just want to show y'all the graph in case anybody was wondering. So once again, there's a vertical asymptote at x equals 3 and a hole in the graph at x equals negative 3, right? We will discuss these types of holes in greater detail later. All right. Y'all want to see another example? Y'all feel like y'all got it? You got it? Good? Got it? You got it? You sure? Ronnie, you good?
Look at the whole list.
All right.
That one was kind of easy.
All right.
So does it matter what's on the top at all? Just same thing as before the main only?
Yeah. All right. If y'all got it, we'll move on. Set the bottom equal to 0. Right? All right. Let's take it up a notch. Right?
The graph with that kind of equation, we don't need, the numerator,
Mhm. You know,
just denominator.
we're gonna get to that. We're not there yet. But yeah, we're gonna get to that. All right, identifying vertical asymptotes of rational functions, right? So by looking at the graph of a rational function, we can investigate its local behavior and easily see whether there are asymptotes, right? We may even be able to approximate their location without even without the graph. However, we can still determine whether a given rational function has any asymptotes and calculate their location. All right, so here we go, vertical asymptotes right now, right? The vertical asymptote of the rational function may be found by examining the factors of the denominator that are not common to the factors in the numerator. So vertical asymptotes occur at the zeros of these factors, right? If there's a common factor in the numerator, that's not a vertical asymptote. Has to be just in a denominator, all right? And a 0. I don't know if I said that. It has to be a 0, right? Y'all know I like to give y'all the T, right? So here you go, right here. I know not everybody gives out the T, but I do, right? So given a rational function, right? Identify any vertical asymptotes of its graph. So here's how you do it, right? Step 1, factor the numerator and the denominator. Step 2, note any restrictions in the denominator, right? Excuse me, note any restrictions in the domain of the function. Sorry about that. Step 3, reduce the expression by canceling the common factors of the numerator and the denominator, right? Note any value that causes the denominator to be 0 in this simplified version, right? These are where the vertical asymptotes will occur, all right? Note any restrictions in the domain where the asymptotes do not occur. These are removable discontinuities, all right? That's the hole in the graph, removable discontinuity, all right? Let's try. Here we go right here. So we want to identify vertical asymptote. So we want to find the vertical asymptote of this graph. Oh, crap. How we do this now? Help me out. What am I going to do? Starts with an F. I'm going to factor it, right? So I have K of X is equal to 5 plus 2 X squared. Can't do nothing with that. Factor the bottom for me real quick. X. 2, 1. Good, good. X and X, right? Give me the signs.
No.
Which one's negative? Which one's positive?
2, negative 2, negative 2, negative 2.
2 minus X
Yeah.
and 1 plus X. I'm gonna get back to y'all. Let me think about that. Nah, it's the reverse. Yeah. This is I'm sorry. This is the minus. Yeah, this is the minus, and then this one is the plus. All right. Negative, it's positive. Yeah, that's it. Okay. All right. What do I do next?
So, negative.
Set them equal to 0, right? So I have 2 plus x equals 0, and I have 1 minus x equals 0, right? So I'm going to subtract 2 from here. What I do to one side, you know I got to do to the other. So I have x1 is equal to negative 2. I'm going to add x over here. What I do to one side, do to the other. So I have x2 is equal to 1, right? Now, let me ask you a question. Were any of the factors in the denominator in the numerator?
Yeah.
They were? No, they're not there, right? So I found my vertical asymptotes, right? They will occur at x equals negative 2 and x equals 1, right? I did. There's nothing I could do with that. Yeah. And that's it. But questions on this though? Are we good? Right. Hmm. Yeah, we're gonna get to that in a second. Uh-huh.
When negative 38 goes to 2, negative 2, negative 2 is 1.
And then 1 to infinity. Yeah. Mhm. That's it. I'm sorry? Like this way? Okay.
But we for the violate that, we also restrict the number in between negative 2 and 1.
Yeah, those are legal. You could plug those in. Yeah, they'll still work. Yeah. You're welcome. In case y'all wanted to see what that would look like, it would look like this. All right. So neither x equals negative 2 or nor x equals 1 are zeros of the numerator. So those two values are two vertical asymptotes. So here you go. You have your negative 2, you have your 1. All right. And those are your vertical asymptotes. Why negative 2?
Yeah.
Then we found negative 2 up here
No, why?
on the graph.
Yeah, they have one on the graph.
Oh, the green?
Yeah.
We didn't even get to that yet. We're gonna get to that. Yeah. That's another conversation. Yeah. But yeah, there's like a lot that we're talking about in this section. We going piece by piece, step by step, right? All right, real quick, let's go back to that whole removable discontinuity, right? Let's talk about that. All right. Occasionally, not all the time, occasionally a graph will contain a hole, right? A single point where the graph is not defined, indicated by an open circle. We call such a hole a removable discontinuity. For example, you have the function f of x is equal to x squared minus 1 over x squared minus 2x minus 3, excuse me, may be rewritten by factoring the numerator and the denominator. So we factor numerator, factor the denominator. I want you to notice something here, right? So you notice how we have x plus 1 right here, right? That's where my removable discontinuity will be, right? Because it's the same in the top and the bottom, right? Now, is there going to be an asymptote at x equals negative 1? No, just a hole, right? But at negative 3, there goes my asymptote, right? There we go. Good stuff, good stuff, good stuff. So notice that x plus 1 is a common factor to the numerator and the denominator. The zero of this factor, x equals -1, is the location of the removable discontinuity. Notice also that x minus 3 is not a factor in both the numerator and the denominator. The zero of this factor, x equals 3, is the vertical asymptote. So there you go. This is how the graph would look here, right? We have our removable discontinuity at x equals -1. And then at x equals 3, we have our vertical asymptote. All right. Questions on this? So this is how you find holes in your graph. Okay. Yeah. So if we were talking domain on this one now, right? All right, this is a pane right here, right? So we're gonna go from -infinity to -1. I'm not including -1, right? And then again, not including -1, going from that to 3, right? Not including 3. And then from 3 to infinity. Yeah. Yeah. Mm-hmm. Hit y'all with a little definition real quick so we can understand this. So removable discontinuities of rational functions. So a removable discontinuity occurs in the graph of a rational function at x equals a, for example, if a is a zero if a is a zero for a factor in the denominator that is common with a factor in the numerator, right? We factor the numerator and denominator and check for common factors. If we find any, we set the common factor equal to 0 and solve, right? This is the location of the removable discontinuity. This is true if the multiplicity of the factor is greater than or equal to that in the denominator. If the multiplicity of this factor is greater in the denominator, then there is still an asymptote at that value. Right? Y'all get that? Y'all don't get that? Wow. Wow. All right. So I have x plus 1 over x plus 1 times x plus 1. Right? So this is what I'm saying. On the bottom, right? In the denominator, x plus 1 has multiplicity 2, right? But you already know that something like this is going to happen. So this is going to simplify down to 1 over x plus 1, right? So what we're saying is if this happens, right? This is an asymptote. This is not a hole, right? The hole occurs when it's the same multiplicity top and bottom. But if the multiplicity is greater in the denominator, that's an asymptote. That's all it's saying. Okay. Really? When you watch the video back, it'll make sense. Don't worry. All right, so check this out. Identifying vertical asymptotes and removable discontinuities for a graph. So here we go. So we want to find the vertical asymptotes and the removable discontinuities for this graph. K of x is equal to x minus 2 over x squared minus 4. Help me out. What do I do first? I heard somebody say factor it, right? And what's the bottom going to be? Perfect, perfect, perfect. All right, so help me out. What's the vertical? Just because the word is there, I'm gonna spell it out. Asymptote. plus 2? No. X equals -2, all right? And if you're wondering how we did that, these will cancel out, right? So we just have the x plus 2, set that equal to 0, subtract 2, subtract 2. That's how you get it, right? X equals -2. That's the vertical asymptote. What about the common factor, right? The common factor, that's going to be my removable discontinuity. All right, I don't know how to spell that. All right, removable discontinuity, right? So what's that going to be? That's 2, right? So x minus 2 equals 0, add 2, add 2. There we go, right? So there'll be a removable discontinuity at x equals 2, all right? At x equals 2. Technically speaking, the removable discontinuity is actually a point, if you really think about it, all right? That's actually going to be a point. But the vertical asymptote is a vertical line. Don't draw a solid line, dash lines for vertical asymptote, right? All right. Just to show you guys what this looks like. This is it right here. So notice that there is a factor in the denominator that is not in the numerator, x plus 2. The 0 for this factor is x is equal to -2. That is the vertical asymptote at x equals -2. And then right here, you see our discontinuity. There it is, right? That's going to be x is equal to +2, right? Okay. Good stuff. Do we want to try another one, or do y'all feel like y'all get it? Get it? Good? Good? All right. It's going to be on YouTube also. Yeah.
Let's see how it's trying to move to this possibility.
Right. That's it. What about the rest of y'all? Y'all good? Want to see another one, or you feel like you get it? Good? All right. Let's keep moving then. Let's keep it moving. So yeah, the graph of this function will have a vertical asymptote x equals -2, but at x equals 2, the graph will have a hole. Yep. All right. Let's talk about identifying horizontal asymptotes, right? I remember we asked about this earlier, right? So while vertical asymptotes describe the behavior of a graph as the output, f of x, gets very large or very small, horizontal asymptotes help describe the behavior of the graph as the input, the x values, right, gets very large or very small. Recall that a polynomial's end behavior will mirror that of the leading term. Likewise, a rational function's end behavior will mirror that of the ratio of the leading terms of the numerator and the denominator functions, right? So there are 3 distinct outcomes when checking for horizontal asymptotes, right? So we have 3 cases. Let's talk about case number 1, all right? If the degree of the denominator, it's on the bottom, right, is greater than that of the numerator, right, then there is a horizontal asymptote at y equals 0. That's simple, right? So if the denominator has a higher degree than the numerator, right, there's a horizontal asymptote at y equals 0. For example, we have 4x plus 2 over x squared plus 4x minus 5, right? X squared is larger than 4x, right? So then there's going to be a horizontal asymptote at y equals 0, right? The x-axis. Set a little differently. All right. Let me show y'all what that would look like real quick. Don't mind me and my colors. I watch a lot of cartoons. So anyway, in this case, right, the end behavior is f of x is similar to 4x over x squared, or that could be simplified down to 4 over x. This tells us that as the inputs increase or decrease without bound, this function will behave similar to the function g of x is equal to 4 over x. And the outputs will approach 0, resulting in a horizontal asymptote at y is equal to 0, right? So here we go. This is how it looks, all right? So this is our function that we had above, right? We're not going to cross that horizontal asymptote except right here. And that's it. So the horizontal asymptote, y equals 0, when f of x is equal to p of x over q of x, where q of x cannot equal 0, right? Where the degree of p is less than the degree of q, right? So the degree of the numerator is less than the degree of the denominator. This is what happens, all right? Let's look at case 2. All right, that's case 1. Let's look at case 2. Most complicated case of all. Oh, Lord, here we go. Help me with this one now. Case 2. If the degree of the denominator is less than the degree of the numerator by 1, we get a slant asymptote. Yikes. All right. So in this case, the end behavior is f of x is similar to 3x squared over x, or equal to 3x, right? This tells us that the input increases or decreases without bound. This function will behave similarly to the function g of x is equal to 3x. As the input grows large, the output will grow and not level off. So this graph has no horizontal asymptote. However, the graph of g of x equal to 3x looks like a diagonal line. And since f will behave similarly to g, it will approach a line close to y equals 3x. This line is called a slant asymptote, all right? So here's what that looks like. And here's what that looks like right here. All right. So to find the equation of the slant asymptote, divide the numerator by the denominator. We all know how to do that. The quotient, the answer that we get out, right? And that's what's going to be the slant asymptote, right? And of course, it's a remainder to blah, 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 right? So the slant asymptote is your quotient when you divide it out, right? So for example, here's the graph that we have here. We have a slant at y equals 3x plus 1, right? And we got that by dividing the numerator by the denominator. Very simple. Questions on this one? It's the most complicated one. Go ahead. The ones that have a slant, they have a numerator that has a higher power than the denominator. Right. If it was reverse, right, it would be y equals 0. Right? Yeah. There are applications of this. I'm just not talking about them because of time. But if you come to tutoring, we can talk about it. You know, I made that way too big. Hold on one second. Sorry about that. Just wanted to show you guys that the slant asymptote is when f of x is equal to p of x over q of x, where q of x does not equal 0, and where the degree of p is greater than the degree of q by 1. All right? So the numerator has a higher degree than the denominator by 1. So if the numerator was x to the 5th, denominator got to be x to the 4th for this to happen. All right? That's simple. Yeah. Has to be less than 1. Right? Nah, that's something else. That's even easier because you know how to do that. You just divide it out and it becomes the quotient, and boom, good to go. All right, last case. All right. We're in law school now. We're dealing with cases. All right. So case 3. If the degree of the denominator is equal to the degree of the numerator, right? There is a horizontal asymptote and y is equal to an over bn, where an and bn are the leading coefficients of p of x and q of x, right? So for f of x is equal to p of x over q of x, where q of x cannot equal 0, right? For example, I have f of x is equal to 3x squared plus 2 over x squared plus 4x minus 5, right? So I'm telling you that there's going to be a horizontal asymptote here at y equals what? 3, right? At y equals 3. So I take the leading coefficient of the numerator, 3x squared. I take the leading coefficient of the denominator, 1x squared, right? Kill those, 3. All right? That'll be your horizontal asymptote. That simple. All right? But that's only when the degree of the numerator is equal to the degree of the denominator. All right? That's our third case. Let me show you guys real quick. So in this case, the end behavior is f of x is similar to 3x squared over x squared equal to 3. This tells us that as the input grows large, this function will behave like the function g of x is equal to 3, right? Which is a horizontal line. As x goes to positive and negative infinity, f of x is going to 3, resulting in a horizontal asymptote at y equals 3, right? And here you go. This is the graph for that, right? Horizontal asymptote when f of x is equal to p of x over q of x cannot equal 0, where the degree of p is equal to the degree of q, right? So the numerator and denominator have the same degree power, right? So we just divide out their coefficients, the numbers that's in front. That's the horizontal asymptote. Okay? Questions on this? It's probably the easiest one. All right. So note that while the graph of a rational function will never cross the vertical asymptote, the graph may or may not cross the horizontal or slant asymptote. Also, although the graph of a rational function may have many vertical asymptotes, the graph will have at most one horizontal or slant asymptote, right? So it'll never have more than one, all right? It should be noted that if the degree of the numerator is larger than the degree of the denominator by more than 1, the end behavior of the graph will mimic the behavior of the reduced end behavior function. For instance, if we had 3x to the 5th minus x squared over x plus 1, right? This end behavior is going to look like 3x to the 4th power, right? Because we just divide them. The end behavior of the graph would look similar, so that an even polynomial with a positive leading coefficient, as x is going to positive or negative infinity, f of x will go to infinity. All right. So good to know, good to know, good to know. All right. That was a lot. Let's put it all together real quick. All right. So horizontal asymptotes of rational functions. The horizontal asymptote of a rational function can be determined by looking at the degrees of the numerator and the denominator. First case, if the degree of the numerator is less than the degree of the denominator, right? Then there's a horizontal asymptote at y equals 0, right? Top is smaller than bottom, right? Y equals 0. If the degree is greater than, right? Excuse me, if the degree of the numerator is greater than the degree of the denominator, right? By one power, right? Then there's no horizontal asymptote. Instead, you have the slant asymptote, right? So x to the 3rd divided by x to the 2nd, slant asymptote, right? X to the 3rd divided by x, right? That's something else. All right, has to be by 1. Last case, the degree of the numerator is equal to the degree of the denominator. That's a horizontal asymptote at the ratio of the leading coefficients. All right. Questions on this? These are the 3 cases right here. All right. Don't worry, there's homework on that. Let's take a look at this. Identifying horizontal and slant asymptotes. All right. So for the functions below, we want to identify the horizontal or slant asymptote. All right. How do I do that again? I forgot. For A, I have g of x is equal to 6x cubed minus 10x over 2x cubed plus 5x squared. What should I do here? Okay, so degrees are the same. I heard that. All right, so 6x cubed over 2x cubed, which gives me 3, right? So horizontal asymptote, I can't spell that word, at y equals 3, right? That's simple. Let's look at h of x. So I have h of x is equal to x squared minus 4x plus 1 over x plus 2. All right. So in this one, the degree of the numerator is higher than the denominator. I'm just going to say numerator degree is higher than denominator degree, whatever. All right. So what should I do here again? It's slanted. Okay. So I have a slant asymptote. Can't spell that word. All right. Keyword here is by 1. Forgot to say that. By 1. So we're gonna have a slant asymptote. And what is the slant? Y equals what? Or tell me how to get the slant. I'll take that too. Divide it out. Good. You can solve it, divide it. All right. So let's see. I have x plus 2 over the x squared minus 4x plus 1. X goes into x squared x times x, x squared, x times 2. This is 2x. I'm going to subtract this. This cancels out. Negative 4x minus 2x, negative 6x. Bring down the 1. X goes into this negative 6 times. This is negative 6x minus 12. Subtract this. This cancels out. This is 13. So my slant is going to be at what? All right, it's going to be a slant at y equals x minus 6. All right. And then, of course, that's it. So that would be some line going across the graph, shifted down 6 units. That's it. Okay. Huh? It can. It can. Yeah. I'm sorry? It's just a remainder. Yeah. I mean, you might need it, but yeah, it's just a remainder. In this particular question, we're just looking for the asymptote. Bear with me 1 second. Okay. So I have k of x is equal to x squared plus 4x over x cubed minus 8. All right, y equals 0. Very good. So denominator greater than numerator. Degree. All right. So horizontal asymptote at y equals 0. All right. Questions on this? Anybody? Sorry about that. Let's see if we really get this. So I want to identify the horizontal and vertical asymptotes of this. All right. So what do y'all want to start with first? Which one? The horizontal or the vertical? Huh? Mm-hmm. You do the opposite? You could. You don't need to though. What was it? Which one you want to start with? The horizontal or the vertical? The vertical? Okay. So I heard vertical asymptote. I can't spell. vertical. Asymptote, right? So what's the vertical asymptote going to be? Or tell me how to get it. Set them denominators equal to 0. So x minus 1 equals 0. Add 1, add 1. X1 equals 1. X plus 2 equals 0. Subtract 2. Subtract 2. X2 equals 0. Excuse me, x equals -2. Sorry about that. And then x minus 5 equals 0. Add 5. Add 5. X3 equals 5. Whew. Questions on this? What about the horizontal asymptote? What is that going to be? No. We'll get to that. Those are the x-intercepts. Right. So what's the horizontal asymptote? Is it? Y equals 0. Okay. All right. I'll vote it. So y equals 0. Because the denominator is 1 power greater than the numerator. Right? Huh? Yeah, so it's 3 vertical asymptotes, but 1 horizontal asymptote. It's x to the 3rd power. Yeah. Yeah. You could kind of just multiply the first term in each binomial, and that'll give you like the leading coefficient right there.
Yeah, that's what I did.
Yeah. Yeah.
And then again, the denominator is
If the denominator is bigger than the numerator, no, like greater than. If the denominator is bigger than the numerator, right, then that's the y equals 0. When they're equal. So if you mean the denominator is smaller than the numerator. So if the denominator is 1 unit, just 1 unit, smaller than the numerator, you get the slant asymptote. But if the denominator is smaller than numerator, but the numerator is like more than 2 units, like say x to the 5th over x plus 1, for example, you're going to do the long division of that, and then there's no horizontal asymptote. What's up? All right. You all want to see, this is how we live in with this question. This is what it looks like. So you see we have our horizontal, like y equals 0. We did cross it over here on the left, and then we have our vertical asymptotes that we'll never touch. Okay.
This is all graph.
Yeah, this is this question here, this function. We want to see another one? Do we feel like we get it? One more? All right. All right, you guys try. So same instructions, find the vertical and horizontal asymptote of the function. Okay. Good.
All right.
So let's start with vertical. How do I do that again? All right. So I have x minus 2 equals 0. X plus 3 equals 0. Add 2, add 2. Very good. Now, none of the factors on the bottom are the same as the top, right? So we good. No, there's no discontinuity, whatever, no holes, right? All right, what about the horizontal asymptote? Okay. C-O-N-T. What is it? Over x squared. So we have what? Y equals 4, right? Not bad. Questions on this? Anybody? Good. All right. Just need to practice it, and y'all be good. All right. Now, back to what you were saying earlier. All right. So we're going to talk about the intercepts of rational functions. All right. So a rational, huh?
Oh, we don't need to.
You don't need to draw it.
Yeah.
Yeah. But you know that there would be a vertical asymptote at 2 and -3, horizontal asymptote at 4, right? And then you could just plug in numbers to figure out what's happening at the left and the right. And that's it. And you draw it. Yeah. All right. Intercepts of rational functions. So a rational function will have a y-intercept when the input, x that you're plugging in, is 0. If the function is defined at 0, that's key, right? A rational function will not have a y-intercept if the function is not defined at 0. Okay? So imagine like 1 over x, right? I can't plug in 0, so there's no y-intercept. That's simple, all right? Likewise, a rational function will have x-intercepts at the inputs that cause the outputs to be 0, right? So since a fraction is only equal to 0 when the numerator is equal to 0, then the x-intercepts can only occur when the numerator of the rational function is equal to 0, period. All right? Nice and simple. Let's try it out. So how do I find the y-intercept here? I don't know. So you're gonna do what? Okay. I like that, right? So for my y-intercept, right? I'm gonna find f of 0, right? So let's see what that would be. 0 minus 2 times 0 plus 3 over 0 minus 1 times 0 plus 2 times 0 minus 5. Let's do a little math on this. What's that? -6. And oh gosh, what's that? +10. Reduce that down a little bit. What's that? Like 3 over 5 negative? Something like that, right? So that's my y-intercept, right? So that's going to be the point where x is equal to 0 and y is equal to -3 over 5, right? 0, comma, -3 over 5. Right? That's my y-intercept. What about my x-intercept? What's that? Right? So I'm gonna have 0 is equal to x minus 2 times x plus 3 over x minus 1 times x plus 2 times x minus 5. Well, I'm not asking about the vertical asymptotes. I'm asking about the x-intercept. Where's the graph gonna cross the x-axis at? So how do I find that? I didn't. How do I find it?
By the numerator.
The numerator, right? I want to set the numerator to 0, right? So I have x minus 2, let me erase the parentheses, is equal to 0, and I have x plus 3 is equal to 0. Solve for that. Plus 2 plus 2. I have x1 is equal to 2 minus 3 minus 3. I have x2 is equal to 3. So what is my x-intercept? Is gonna be what? 2, 0 and 3, 0. Just like that, right? Remember, x-intercept, y-intercept are points, right? They're points on the graph. So that's why I have to write them like that as an answer. Questions on this? You good?
With that first coordinate we had.
This is the y-intercept. Yeah. You could also write it in words if you want. Like if you want to say like the y-intercept is 0, -3/5, and the x-intercepts are 2, 0 and 3, 0. You could, spice it up with words if y'all want. Yeah. Sure. Problem. Provided it doesn't make the denominator 0. But what if it did? What if it made the denominator 0? What would that be? It'd be a what? No, it's a function. Like say there was a number that I could plug in that would make the numerator 0 and the denominator 0. What would that look like in the graph? That would be a no. It would be we just did this. It would be yes.
Yeah.
It'd be a hole. All right. Yeah. Removable discontinuity. Yeah. AKA a hole. All right. All right. Fun stuff. Fun stuff. In case you're wondering what this might look like, it looks like this. All right. So we have our horizontal asymptote, y equals 0, vertical asymptotes here. But what we're focusing on right now, right? We have the y-intercept, 0, comma, they got negative 0.6, whatever. We got -3/5, same thing, right? And then we have our x-intercept at -3, 0, and we have our other x-intercept at 2, 0. I want to talk about this one right here. You see that -3, 0 right here? Had we not had that, we wouldn't even know that this graph would cross the horizontal asymptote. This is how you can tell when it crosses, right? Because you're gonna have an intercept that's gonna do it, right? Same thing over here with the 2 and the 0, right? And then to figure out like what's happening with this, just kind of plug in numbers. You get like little points and you can kind of estimate what's gonna happen there. All right. If I was gonna draw this rawly without like a calculator or something, I would definitely want to point out. When I say point out, I mean label, right? That's really important. Label your graphs, right? I want to label the x-intercepts, label the y-intercept, right? Label those vertical asymptotes. Like don't make a strong line. You want like a dash line for that, right? Dash line for the horizontal asymptotes as well. And then use your imagination. What's gonna happen? Right? All right. Now to your question, all right? We've been building up to it all night, right? Graphing rational functions, all right? So the last example, we see that the numerator of the rational function reveals the x-intercepts of the graph, whereas the denominator reveals the vertical asymptotes of the graph, right? As with polynomials, factors of the numerator may have integer powers greater than 1. Fortunately, the effect on the shape of the graph at those intercepts is the same as we saw with polynomials, all right? So some good news there. It's the same kind of effect they're saying, basically, right? So let's look at this real quick. The vertical asymptote associated with the factors of the denominator will mirror one of our two toolkit functions, right? Reciprocal functions. When the degree of the factor in the denominator is odd, the distinguishing characteristics is that of one side of the vertical asymptote. The graph heads towards positive infinity on the side of the graph heads, and on the other side of the graph heads towards negative infinity, right? So remember this graph, the 1 over x, right? So it's going to mimic that. Or it'll mimic this, all right? So when the degree of the factor in the denominator is even, the distinguishing characteristics is that the graph either heads towards positive infinity on both sides of the vertical asymptote or heads towards negative infinity on both sides of the asymptote. All right? So that's like our y equals 1 over x squared. All right? Let's look at an example real quick. All right? I want to make this too big, right? So we have f of x is equal to x plus 1 squared times x minus 3 over x plus 3 squared times x minus 1, right? So we know that there's going to be what? When I look at the top, I have x squared, I have x to the second, and I have x as x to the third. On the bottom, I have x to the third as well, right? So the powers in the numerator and the denominator are the same. So I just got to divide them out, right, to get the horizontal asymptote, y equals 1. Bam, there it is, right? Set the denominators equal to 0, right? You have x plus 3 squared equal to 0, and then x minus 2 equal to 0. I noticed that those denominator factors are not on the top, so therefore those are the vertical asymptotes, right? Solve for them, even though it has multiplicity 2, we already know what's going to happen. Vertical asymptote, right? At x equals negative 3 and x equals 2, right? Let's go back to that for a second, right? X plus 3 has multiplicity 2, right? So at multiplicity 2, look at how this graph goes, right? Both of them go to infinity on left and right, right? But on the 2, right, which is just like 1 over x, one side goes to infinity, the other side goes to negative infinity. That's another way we could tell. Next thing we gotta talk about x-intercepts, y-intercept, right? That's how we're gonna know if we're gonna cross an asymptote, right? So to get the x-intercepts, we set the numerator equal to 0, right? So x minus 3 equals 0 is gonna be x plus 3, right? So right here, there goes one of our x-intercept. X plus 1 squared, we're gonna set that equal to 0, right? Little math, boom, 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 we get x equals negative 1, right? That's our other x-intercept. For our y-intercept, just plug in 0 for everybody and let's see what happens, right? The numerator is going to go to -3. Denominator is going to be 9 times -2, -18, right? Can kind of reduce that a little bit, right? So that's like what, 1/6, something like that. So boom, here that is. And that's going to be our y-intercept. You just got to make sure that when we're doing an x-intercept, y-intercept, we got to touch it. Graph got to go through it. All right. And then that's it. Graph it as best you can. As best you think, whatever you think is going to happen. If you use your graphing calculator, you can get a more accurate idea of what's happening. Right? That's that. Fun stuff.
If we're on the big graphs, so we're testing, we like, put it blank for the X, Y, and stuff, draw out the horizontal, vertical,
Lines. Yeah. And then just do your best to guess what it's going to look like. Or if you have a calculator, type it in. Whatever.
and calculate the library, right?
They do. For free. So at the x-intercept, just want to recap, right? At the x-intercept, x equals -1 corresponding to the x plus 1 squared, right? Factor of the numerator, the graph bounces, right? Consistent with the quadratic nature of a factor, right? So right here, -1, right? It's bouncing right off of it, right? Because it's quadratic. Okay? At the x-intercept, x equals 3, corresponding to x minus 3, right? The factor of the numerator, the graph passes through the axis as we would expect with a linear function, right? So right here, 3, we're passing through that axis, right? At the vertical asymptote, x equals -3, right? Corresponding to x plus 3 squared, factor of the denominator. The graph heads towards positive infinity on both sides of the asymptote, consistent with the behavior of the function 1/x squared, right? That's what happens 1/x squared. They both go to infinity. At the vertical asymptote, x equals 2, corresponding to x minus 2, factor of the denominator, the graphs head towards positive infinity on the left side of the asymptote and towards negative infinity on the right side, right? There you go. Positive infinity on the left side, negative infinity on the right side. And that's it. All right. Once itself. Go ahead. So with the horizontal, right? They have the same powers in the numerator and the denominator. Let me scroll up real quick. Wait, no, it's right here, right? So they have the same powers in the numerator and denominator, right? It's x to the third power, right? In the numerator and denominator. So I take the coefficient of the numerator and the coefficient of the, excuse me, let me say that again. I take the coefficient of the leading term in the numerator and the coefficient of the leading term in the denominator, divide those, and then that's going to be the horizontal asymptote. Yeah.
So this is
But you know I can't leave y'all hanging without giving y'all the tea first, right? Make it a little bit easier, you know? Tell y'all how to do it. All right, so given a rational function, you want to sketch the graph. This is how you do it step by step. Step 1, evaluate the function at 0 and find the y-intercept. Plug in 0 for all the x's, get the y-intercept. Boom, right? Step 2, factor the numerator and the denominator. So factor them out. Boom, boom, right? Step 3, for factors in the numerator not common to the denominator, determine where each factor of the numerator is 0, and that's your x-intercepts. Boom, right? Step 4 now, right? So find the multiplicities of the x-intercepts to determine the behavior of the graph at those points, right? So remember, if it's an even multiplicity, bounce, right? Odd multiplicity, we're going through it, all right? All right. For factors in the denominator, note the multiplicities of the zeros to determine the local behavior, right? So odd multiplicity, right? What's happening? One's going infinity, one going negative infinity, right? Even multiplicity, right? We both going either positive or we both going negative, whatever, depending on the question. Right? Where was I? Step 5. The factors in the denominator, note the multiplicity of the zeros to determine the local behavior. For those factors not common to the numerator, find the vertical asymptotes by setting those factors equal to 0 and then solve, right? So that's the vertical asymptote. Step 6, for factors in the denominator, common to the factors in the numerator, find the removable discontinuities by setting those factors equal to 0 and then solve, right? That's when they have the same factor in the numerator, the same factor in the denominator. That's a hole in the graph, right? Okay. Step 7, compare the degrees of the numerator and the denominator to determine the horizontal or the slant asymptote, right? So slant asymptote, there's a difference in the degree by 1, right? Horizontal asymptote, right? Then they're going to be equal, right? And then, of course, 8, sketch the graph, whatever. Right? Questions on this? Those of you that don't have the graphing calculator, to help you sketch the graph, you can do a table of values. You can plug in numbers and see what happens to them over time, and that will help you to draw the graph. All right? Just remember what you have to touch, what you have to cross, all of that good stuff.
We need to drive the graph tomorrow.
Hmm? Not for a lot, though. It's like one question on that. It is. I agree. Not my favorite thing to do, but it is what it is. Oh, let's try it. Lord help me. So we're gonna sketch this graph, right? What should I do first again? I forgot. All right, let's find that y-intercept, right? So that y-intercept. So I'm gonna find f of 0, which basically I'm just plugging in 0 for everything, right? So it's gonna be 0 plus 2 times 0 minus 3 over 0 plus 1 squared times, 0 minus 2. I almost made a mistake there, right? So this becomes what? 2 times negative 3, call that negative 6. This is like what? 1 times negative 2, call that negative 2. Let's call that 3, right? So I have a y-intercept, right? At, what's that point? 0, 3. All right. We'll come back to that. What about my x-intercept? All right. So I'm going to set the numerator equal to 0. So x plus 2 equals 0 and x minus 3 equals 0. I have no idea why I did parentheses there. I'm going to subtract 2 from here. I do the one side, do to the other. I have x equals negative 2. And then I'm going to add 3 over here where I do the one side, do to the other. So I have x2 is equal to 3. So what are my x-intercepts? I have negative 2 comma 0, and I have 3 comma 0. Did I lose anybody so far? You're good. All right. Let's talk about asymptotes. Which one we want to start with? All right, let's do the vertical asymptote, step 3, right? Let's do that vertical asymptote. So vertical, right? Set the denominators equal to 0. I noticed that the denominators and the numerators don't match, so we're blessed, right? So I have x plus 1 squared equals 0. And let me just solve for 0. So this is going to be square root, x plus 1 equals 0, subtract 1, right? So what do I have? X is equal to -1, right? So that's a one vertical asymptote. Other vertical asymptote, x minus 2 equals 0, add 2, add 2. So what do I have? X is equal to positive 2, right? Those are my vertical asymptotes, right? Let's talk horizontal asymptote. So what is this? Looks like my denominator is bigger. So what is that going to be? And is it bigger by 1? Okay. Yeah, bigger by 1
The denominator
is
bigger
bigger.
than
So what is it?
y.
Y equals 0. Okay. The horizontal asymptote, y equals 0. Just gonna say because, right? Numerator. I'm just gonna do this. Numerator is like x squared. Denominator is like x cubed. Call it a day at that, right? And that would be similar to 1 over x. All right? Okie dokie. Let's put this all together, shall we? I'm sorry?
Denominator and denominator is greater than 1.
If the denominator is bigger than the numerator, then it's y equals 0. In general, it doesn't matter. It's the reverse by 1.
So then
Yeah.
greater by 1.
Right. Then it's slant. It's y equals 0. Yeah. Yeah. By 1, then the quotient is going to be the slant asymptote. Right? If the numerator is even bigger than that, right? Just do the division and whatever. That's your graph. All right. All right, let's make this happen real quick. Oh Lord. All right, so we're gonna have to get some colors up in here. There's gonna be a little mix, right? What was number 1? Y-intercept. All right. All right, I'm just gonna go straight across. Just going straight across right here. Y-intercept. So we had, what was it? I forgot. 0, 3, right? So x is 0, go up 1, 2, 3 right here. That's that y-intercept. What's that? 0, 3. Let's look at number 2. X-intercepts. I have -2 and +3. All right. 1, 2 right here. So this is, what's that point again? -2, 0. And I think the other one was +3, right? 1, 2, 3. Let's call that 3, 0. All right. Can I scroll now? I'm good. All right. Next, let's talk vertical asymptote. I need another color for that. Let's go purple. All right. Did I use orange already? Yeah, I did. All right, let's talk vertical asymptotes. So I have x equals -1. So right here, dash line. I ain't got no ruler, so that's why it looks so funny. All right. And then x equals 2. Let me see where 2 is right here. So, all right. No ruler. That's why it looks like that. All right, let's talk horizontal asymptote. Y equals 0. I'm just going to copy them with their green. All right, so this is y equals 0. I should have definitely labeled this and nobody said nothing. Oh, man. Got points off on the exam and nobody said nothing. Come on. This is y equals 2. Excuse me, x equals 2. And then this is x equals -1. All right. All in colors. All right. So that being said, right? Let's graph this bad boy. Right? After this, it just becomes table of values. Plugging in numbers to see what happens, right? I need another color. 1 second. Did I do blue yet? Let's do blue. All right, so I know that I'm gonna cross the x-axis at -2, right? I know that's happening. All right, x-intercept -2, right? Trying to look. So at -1, so I'm looking at the function right here, right? Everybody sees that x plus 1 is squared, right? So we have an even, what am I trying to say? I have a second degree multiplicity, right? Even multiplicity. So we know that what's going to happen? Both infinity or both negative infinity, right? That's happening at -1, right? So how do I know whether this is going to go positive infinity or negative infinity? Just going to plug in some numbers. Let's see what happens at, what am I interested in? I'm trying to think. -3. I want to know what happens to the function at, so I want to know what happens at f of -3. And I kind of want to know what happens at f of, let's say 1.5, -1.5. This will help me to determine what it's going to be, right? So f of 3, you know what? I should just copy down this function right here. You can see why I hate doing this, right? It's a pain. Yeah. X plus 2, x minus 3. Hold on. X plus 1 squared, and I forgot what the other one was. X minus 2. Okay. I'm trying to find the y value of that so I can determine. Let me just check one time. Was that -2? Yeah, it was. I want to find the y value so I can determine where it's going on the graph, right? Okay, so f of -3, right? I don't really care what the answer is. I more care what is the sign of the answer. That's what I really want to know. All right. So this is like -3 plus, I made a mistake. -3 plus 2. This is like -3 minus 3, right? This is like -3 plus 1. Doesn't even matter because that's squared. And then this is like -3 minus 2, right? Let me see. This is a negative. This is a negative. You know that's a positive. And that's a negative, right? A negative times a negative is a positive. A positive divided by a negative is a negative, right? So I know that this is negative, right? So what does that mean, right? That means that I'm right. Mm-hmm. That means that I'm somewhere down here, right? That's what I'm predicting. Let me just verify real quick. F of negative 1.5. Let's look at that, right? So this is going to be negative 1.5 plus 2, negative 1.5 minus 3. This is going to be negative 1.5 plus 1 squared, negative 1.5 minus 2, right? Again, I don't really care what the answer is. What is a sign? That's what I care about, right? So negative 1.5 plus 2, that's a positive, right? Negative 1.5 minus 3, that's a negative, right? Negative 1.5 plus 1 is negative, but it's squared, so whatever is positive, right? And then negative 1.5 minus 2 is a negative, right? A negative divided by a negative is a positive, right? Also, positive times a negative is negative. Y'all get the idea, right? So anyway, that's positive, right? So I can confirm right now that this is happening, right? This is coming from negative infinity. It's going to cross the x-axis there. This is going to go up. If that's going up, what's happening on the inside right here, right? You already know this is going to happen. We coming from positive infinity, right? How do I know that? Because of the multiplicity being 2, right? Okay. Now, let me go back up here. X minus 2 has one as a multiplicity, right? It's odd. So we know we're going through the x-axis at that point, right? Well, we're not going to go through it, but we're going through the x-axis at some point. So let's think about what's going to happen here. Is there a bounce? I would say we're going to cross the y-intercept, but I need to check something. That's 2, that's 1. I want to check positive 1.5. Let's do f of positive 1.5, right? So this is going to be 1.5 plus 2 times 1.5 minus 3 over 1.5 plus 1 squared times 1.5 minus 2, right? This is positive. This is negative. Of course, that's always positive. And this one is going to be negative, right? Negative divided by negative is positive, right? So I know 1.5 is in between 1 and 2, so that's positive, right? So I know that this is happening over here, right? Let's see what else is going on, right? I know I'm going to cross at 3, 0, right? Trying to figure out what we're going to do. What we could check also. You know what I'm curious to see? I'm curious to see 0.5. Let's look at that. F of 0.5. So this is 0.5 plus 2, 0.5 minus 3, 0.5, whoops, plus 1 squared, and then 0.5 minus 2, right? This is positive, this is negative, positive always, and then this one is negative. That's positive too. So I know something weird is going on here. I don't know if it's something like this. I'm not sure, can't tell, but something like that is going on right there. All right? Huh? I'll look at it after. I'll look at it after. I'm probably doing something wrong with this. I don't know. Yeah. It's basically the same. All right. Got you. Well, we just sketching here. It probably should drop down lower, right? Because it's supposed to go to the horizontal asymptote and then go up. So that kind of makes sense. That'll go down a little bit lower, right? And then what I want to see is what's happening between 2 and 3. All right. I know I'm going to cross at 3, but what's happening between 2 and 3? So I'm looking at 2.5. That's what I'm thinking about. So I'm thinking about f of 2.5, right? Let's take a look at that. So 2.5 plus 2, right? Again, I don't care what the answer is. I just care what the sign is, right? So 2.5. Let me see, minus 3. You said it's going to go down?
No,
Huh? And let me see, 2.5 plus 1 squared, and I have 2.5 minus 2. Let's check it out. This is positive. This is negative. This is always positive. And then this one is positive. So that's going to be negative, right? Boom. So I know that right here is negative. So I'm thinking we're going to come up. I'm thinking something like, draw for me. I'm thinking something like this is going on, right? I might be wrong. But something like that I feel like is going on. Agree?
Once it goes to uh says it stays at 0.
Stays at 0? Gotcha. Oh, right. Horizontal asymptote, right? So boom, like that. That makes sense. Right? And then we could confirm that by checking out, let's say 4, for example, right? So last one. Let's say we want to do f of 4, right? This would be 4 plus 2, 4 minus 3. And if it was 5 or something, the same kind of thing is going to happen as well. So that's why I don't need to do so much. This would be 4 plus 1 squared, 4 minus 2. Let's take a look at that, right? 4 plus 2, positive. 4 minus 3, positive. This one is always positive. This was positive, right? So boom. Right? So I know that I'm above the x-axis at best, right? And then if you actually get the numbers, you will see this happening. So boom, there goes your graph right there. Couple of things that I want to make note of, right? Notice how my graph is labeled. I have the asymptotes labeled. I have the y-intercepts labeled, right? On your test, you label your graph, all right? Don't just draw the graph and say that's it, right? I need to see key points. I need to see the intercepts, right? I need to see what is the vertical asymptotes, all right? If you want, go a step further, you could label the points on the graph itself. I'm not asking for all that. But if you want to go further, go right ahead. All right? And that's it. Questions on this?
But you said like, the last one, so like, half point equals the button before. That means that y is 4 and x equals this.
X equals 4. Yeah, like the last one, right? F of 4. Yeah, so x equals 4. And then the y value is whatever that
Whatever
contraption is. Yeah. But in actuality, for me, I don't really care about that. I kind of just want to know what is the sign of it. If the sign was positive, I know I'm above the x-axis. If sign was negative, I know I'm below the x-axis. That's all I care about. Hmm?
all big points of that. So, methodology.
Right. And then use the function to help you with it, right? You know that at a even multiplicity, both are going to infinity or both are going negative infinity. Odd multiplicity, we going straight through that x-axis. You know? Last minute questions on this? Are we good? Good? All right, let's move on. Wait, all right, got you. Go ahead. And I know I can't draw that well, but it was supposed to look like this. I tried. This is the actual graph that we're supposed to have. All right. Yeah. I tried. I'm not a computer, so I can't get it. I can't get it like pretty like this, but something like this. All right. New topic. Easier topic. Hallelujah. All right. Oh, that's it. That's it. So India, right, is the second most populous country in the world with a population of about 1.39 billion people in 2021 after COVID, right? The population, right, is growing at a rate of about 1.2% each year. At this rate, if this rate continues, the population of India will exceed China's population by the year 2027. That's like 2 years from now, right? When populations grow rapidly, we often say that the growth is exponential, right? Meaning that something is growing very rapidly. To a mathematician, however, the term exponential growth has a very specific meaning. In this section, we'll be looking at exponential functions, which model this kind of rapid growth. All right. This is fun stuff right here. Yeah. That's what we're leading up to, that thing. All right. So we're gonna be, identifying exponential functions. So when exploring linear growth, we observed a constant rate of change, a constant number by which the output increased for each unit increase in input. For example, in the equation f of x is equal to 3x plus 4, the slope tells us the output increases by 3 each time the input increases by 1. Right? So the scenario in the India population example is different because we have a percent change per unit of time rather than a constant change in the number of people. So defining an exponential function, a study found that the percent of the population who are vegans in the United States doubled from 2009 to 2011. In 2011, 2.5% of the population was vegan, adhering to a diet that does not include any animal products, no meat, poultry, fish, dairy, eggs. So sad. If the rate continues, right, vegans will make up 10% of the US population by in 2015, 40% in 2019, and 80% in 2021, right? Y'all could go vegan if y'all want. I like my meat. Go ahead. Right? Anyway, right? What exactly does it mean to grow exponentially, right? What does the word double have in common with percent increase, right? So people toss these words around errantly, right? Are the words used correctly? The words certainly appear frequently in the media. Percent change refers to the change based on a percent of the original amount. Exponential growth refers to an increase based on a constant multiplicative rate of change over equal increments of time. That is a percent increase of the original amount over time. Exponential decay refers to a decrease based on a constant multiplicative rate of change over equal increments of time. That is a percent decrease of the original amount over time. All right. So that's what we're getting into. Right. Technically speaking, it's kind of impossible, because you're always taking a piece of a piece of a piece of a piece, But you'll learn more about that in calculus. All right. For us to gain a clear understanding of exponential growth, let us contrast exponential growth with linear growth, right? We will construct two functions, right? The first function is exponential, this one, right? We start with an input of 0 and increase each input by 1, right? We will double corresponding, right, consecutive outputs. The second function is linear, right? G of x equals 2x, right? We will start with an input of 0 and increase each input by 1. So we will add 2 to the corresponding consecutive outputs, right? So here's what happens, right? So for my exponential function right here, I have x for 0, 1, 2, 3, 4, 5, 6. And as I plug in each x value, this is what happens to the numbers. This is how it grows. 1 to 2 to 4 to 8 to 16 to 32 to 64. But with linear growth, see how it goes. Like when I plug in 0, right, is 0. Or when I plug in 1, I have 2, then 4, then 6, then 8, then 10, then 12, right? So linear growth grows slower than exponential growth. At first, they look the same, but they change over time, right? So from table 1, we can infer that these two functions, exponential growth, dwarfs linear growth, all right? So that's what we want with our money. We want exponential growth of our money. All right? All right, so exponential growth refers to the original value from the range increasing by the same percentage over equal increments found in the domain. Linear growth refers to the original value from the range increasing by the same amount over equal increments found in the domain, right? Apparently, the differences between the same percentages and the same amount is quite significant. For exponential growth over equal increments, the constant multiplicative rate of change resulted in doubling the output whenever the input increased by 1. For linear growth, the constant additive rate of change over equal increments resulted in adding 2 to the output whenever the input was increased by 1. The general form of the exponential function is f of x is equal to a times b to the x power, where a is a non-zero number and b is a positive real number not equal to 1. All right? So if b is greater than 1, the function grows at a rate proportional to its size. If 0 is less than b, which is less than 1, the function decays at a rate proportional to its size, right? So when b is 1, we have growth. When b is less than 1 fraction, we have decay. All right? So let's look at the function f of x is equal to 2 to the x from our example. We'll create a table here to determine the corresponding outputs over an interval, let's say from -3 to 3. So we plug in -3, we have 1/8, -2, 1/4, -1/2, 0 is 1, then we have 1 is 2, 2 is 4, 3 is 8. All right, that's how it changes over time. There is a graph associated with this. All right. This is how that graph looks. I'll show you guys. Now we can examine this graph. So let us examine the graph by plotting the ordered pairs we observe, and then we make a few observations, right? So -3, 1/8 is right here. -2, 1/4. -1/2, right? Then we have 0, 1, and 1, 2, 2, 4, 3, 8. So boom, this is our exponential graph right here. All right, so as we go to -infinity, we go really, really close to the x-axis, but we never actually touch it. That's like a horizontal asymptote right there. And then we go wild when we go to infinity. All right.
This will be in the exam.
Nope,
Yeah.
exam 3. Next week, Thursday. So let's define the behavior of the graph of the exponential function. So f of x is equal to 2 to the x. right? And highlight some of its key characteristics, right? So the domain of the exponential function is actually negative infinity to positive infinity. The range is 0 to infinity, right? And as x is going to infinity, right? The f of x, the y is going to infinity. As x is going to negative infinity, the f of x goes to 0. All right. F of x is always increasing. The graph of f of x will never touch the x-axis because base 2 raised to any exponent never has a result of 0, right? Y equals 0 is the horizontal asymptote, and the y-intercept is 1. All right? Good stuff to know. Let me generalize it for you guys to make it a lot easier and clearer. Little definition. So exponential function. So for any real number x, an exponential function is a function of the form f of x is equal to a times b to the x power, where a is a non-zero real number called the initial value, right? And b is any positive real number such that b does not equal 1. The domain of f is all real numbers. The range of f is all positive real numbers where a is greater than 0. The range of f is all negative real numbers if a is less than 0, excuse me. The y-intercept is 0 comma a, and the horizontal asymptote is y equals 0. Make sense? All right. You guys might have seen this in science class already, so I totally get it. Let's look at this example. So I want to identify exponential functions. Which one of these are not exponential functions?
The GFF,
G of x. Okay, why?
because they are three in the top
Mhm.
of the X.
Okay. Right, x to the third power is a polynomial cubic function, right? The other ones are exponential functions. You have a number raised to a variable. That's an exponential function. All right? Good job.
Maybe,
No, that's exponential because the x is in the power. All right?
so the H and I are not.
H and J are exponential.
Yeah.
Yeah. Because you have a number and then it's raised to a variable power.
So which one is it? They're all are.
G is not. G is not an exponential function. Just to make me feel good though, let's do another one. All right? Which of these is not an exponential? Or which one is an exponential? How about that? G of x is exponential?
Only the second. Well, technically not the last one. Yeah, not negative function. Within the F of it.
Why? Okay. Okay.
Yeah.
Yeah. Remember when I had the 2 to the x, I had a negative power there? It just means it's going to like 0, you know?
Not the last one.
The last one, J of x and G of x. All right? The other ones are not. Those are some other things. All right? Polynomials and linear. No, that's fine. Yeah, I can have a negative power. So think of it like if I had y equals 2 to the x, right? I could have y equals 2 to the negative 1 power. You know, that's just half. That's cool. Yeah, that's fine. Yeah. All right, good stuff. Good stuff. Well, speaking of which, let's talk about evaluating exponential functions right now. So recall that the base of an exponential function must be a positive real number other than 1, right? Why do we limit the base b to positive values? To ensure that the outputs will be real numbers, all right? Observe what happens if the base is not positive. Let's say that b was -9 and x is equal to a half, right? Then f of x is equal to f of a half, which is -9 raised to the half power. That's the square root of -9. That's not a real number, you know? So why do we limit the base to positive values other than 1? Because base 1 results from the constant function. Observe what happens if the base is 1. Let b equal to 1, right? So f of x equals 1 to the x power, which is equal to 1 for any x value, right? So it can't be equal to 1, right? To evaluate an exponential function of the form f of x equal to b to the x, we simply substitute x with the given value and calculate the resulting power. For example, let f of x equal 2 to the x, where what is f of 3, right? So very simple, just plug in 3. 2 to the third power, that's 2 times 2 is 4, 4 times 2 is 8, boom, that's it. All right? Easy peasy. Right? So to evaluate an exponential function of the form other than the base form, it is important to follow the order of operations. For example, let f of x equals 30 times 2 to the x power. What is f of 3, right? So you plug in the 3, right? So it's going to be 2 to the third, which is 8, right? And then 8 times 30 is 240. Boom. All right. So note that if the order of operations was not followed, something like this could happen where you have 30 times 2 to the third power, right? Which is not equal, it does not equal 60 to the third. All right. But you guys are good. Y'all math 30. Y'all know order of operations and all that. Please excuse my dear Aunt Sally, all that good stuff. All right. On the test, it's on your formula sheet. All right. So let's define exponential growth. Because the output of exponential functions increase very rapidly, the term exponential growth is often used in everyday language to describe anything that grows or increases rapidly. However, exponential growth can be defined more precisely in a mathematical sense. If the growth rate is proportional to the amount present, the function models exponential growth. Very simple, right? So here's the exponential growth function right here. So a function that models exponential growth grows by a rate proportional to the amount present. For any real number x and any positive real number a and b such that b does not equal 1, an exponential growth function has the form f of x is equal to a times b to the x power, where a is the initial or starting value of the function, and b is the growth factor or the growth multiplier per unit raised to the x power, right? All right. Let's talk about finding equations of exponential functions. All right. So in previous examples, we were given an exponential function, which we then evaluated for a given input. Sometimes we're given information about an exponential function without knowing the function explicitly. We must use the information to first write the form of the function, then determine the constants a and b, and evaluate the function itself, right? So let me give y'all a little bit of tea real quick. Because you know I can't leave y'all hanging. I can't do that. So here you go. This is how to do it right here, right? So given two data points, right? We want to write an exponential model. This is how we do it. If one of the data points has the form 0, comma a, then a is the initial value, right? Using a, substitute the second point into the equation f of x is equal to a times b to the x and solve for b. If neither the data points have the form 0, comma a, substitute both points into the equation with the form f of x is equal to a times b to the x, solve the resulting system of two equations in two unknowns and find a and b, right? Step 3, using the a and b found in the steps above, write the exponential function in the form f of x is equal to a times b to the x, all right? Fun stuff, fun stuff, fun stuff. All right. Let me give y'all a little bit more tea. Because tea is good for you. All right. So, given the graph of an exponential function, let's say that we wanted to write an equation from the graph, right? Here's how you do it. First, identify 2 points on the graph. Choose the y-intercept as one of the 2 points whenever possible. Try to choose points that are as far apart as possible to reduce round-off error. That's key, right? Step 2, if one of the data points is the y-intercept 0, comma a, then a is the initial value. Using a, substitute the second part into the equation. F of x is equal to a times b raised to the x power, and then solve for b. If neither of the data points have the form 0a, substitute both points into two equations with the form f of x is equal to a times b to the x. Solve the resultant system of two equations in two unknowns to find a and b, and then write the exponential function f of x is equal to a times b to the x power. Good stuff, good stuff, good stuff. All right. Let's talk about money. Right, great talk. So we're gonna be talking about compound interest, all right? Applying the compound interest formula. So saving instruments in which earnings are constantly reinvested, such as mutual funds and retirement accounts, use compound interest, right? The term compounding refers to interest earned not only on the original value, but on the accumulated value of the amount. The annual percentage rate, APR, of an account, also called the nominal rate, is the yearly interest rate earned by an investment account. The term nominal is used when the compounding occurs a number of times other than the once per year. In fact, when interest is compounded more than once a year, the effective interest rate ends up being greater than a nominal rate. This is a powerful tool for investing, right? So we can calculate the compound interest using the compound interest formula, which is an exponential function of the variable time t, principal p, APR y, and the number of compounding periods in the year. So, right, our final account balance, whatever, A of t, right, would be equal to our principal, the amount that we started with, times 1 plus the interest rate divided by the number of times the rate will be applied, raised to the number of times that the rate will be applied, times the time in years. How many years are we investing this thing for? Right? This is the compound interest formula right here. All right. Some vocabulary that we gonna need. R is your interest rate, right? Like, you know, when your bank be like, oh, you could get 0.0258 percent interest per year. Yay. All right. Can't even get a whole percent. All right. So for example, observe this table right here, right? Which shows the result of investing $1,000 at 10% interest for 1 year. Notice how the value of the account increases as the compounding frequency increases, right? So if you ever hear someone say annually, right? Annually is like per year. So it's gonna increase by $100, right? After 1 year, right? Our rate is 10%, of course, right? So 10% of 1,000 is 100. So that's how it increased by 100, right? Semi-annually, right? Is what? Yeah, that's 6 months. Yeah. So, well, actually, no. Let me think about that. Semi-annually. Yeah, twice a year. Yeah. But why is it so small? That don't make sense. The numbers don't make sense for semi-annually. All right, hold up. I'm gonna Google that. Twice a year or every 6 months, yeah.
Oh, so
Yeah. That doesn't make sense though, because in the first 6 months, you would get the 10%, so that's 1,100. But then you would have to do another one, right? Yeah. Yeah.
Open by yourself. Then it comes to me the kind of the extra.
Got you. Got you. All right. Quarterly, every 3 months, 4 times for the year, right? Monthly, 12 times, right? And when I say like 12 and all of that, that's the N in the formula, right? For the compound interest formula. Daily, 365, sometimes 366. Huh? What's up? Mhm. T is how many years you're gonna do it for. Yeah. Depends. So if it was 1 year, T is 1, right? But N could be any one of these, depending on how it's compounding. Yeah. So if it's annually, then N is 1, right? Semi-annually, N would be 2, right? Quarterly, N would be 4, right? Monthly, 12. Daily, 365. Sometimes 366. Okay. Right?
not gonna do that's right.
Huh?
That's right.
This is such a scam waiting.
It is.
So scary. Like how can you guarantee me infinite returns? Infinity is damn near impossible.
But their percent is like
So
stupid low. Like they have a decimal of a percent.
Yeah.
Like literally you'd have to have like $1 million to see like a couple of dollars, like per month type of thing.
Even
Right?
that, they should have to say.
It never will be. Never will be. Yeah. 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 True. Mm-hmm.
Well, they're telling you like,
Right.
like
Then they push all their money offshore so they don't have to pay taxes. Yeah.
HPRC like 4.75 ish, but if inflation goes up 5% every year.
That's nothing. That's nothing. Yeah.
You end up actually losing money over like the 10 years for money in there.
It's true.
Numbers increase.
True. True. All right, let's look at this, right? This is the compound interest formula right here. So compound interest can be calculated using the formula A of t is equal to the principal, right? Times 1 plus the rate divided by the number of times compounding raised to the nt power, right? A of t is your account value. That's like your final account value. T is your time measured in years. P is your starting amount of the account, often called the principal or generally present value, right? R is your annual percentage rate, your APR, right? Expressed as a decimal, right? So if it was like 4%, we're talking about 0.04. That's what that means, right? And N is the number of compounding periods in 1 year, right? Using that vocabulary that we just saw, right? Good stuff, good stuff. Then, I feel like you guys can figure out how to play around with that formula since we are in Math 30. Let's talk about evaluating functions with base E, all right? So as we saw earlier, the amount earned on an account increases as the compounding frequency increases, right? Using that table. Shows that the increase from the annual to semi-annual compounding is larger than increasing from monthly to daily compounding. This might lead us to ask whether this pattern will continue. Examine the value of $1 invested at 100% interest for 1 year, compounding at various frequencies, right? And here you go, right? So I'm starting off with $1, right? That's why you don't see P there, it's just 1, right? And then we're gonna, I'm looking at the annual right now, right? So the rate is 100%, so that's 1, divided by the number of times we're gonna do this, which is 1. And we're going to do that for a year, right? 1 time. So boom, that became $2. Nice, right? Semi-annually. Now, we have our $1 that we're starting off with. That's the number in front here. Not this one that you see here. It's a 1 that's in front out here, right? And then we're going to be compounding this twice at a rate of 100%. Right? Raised to the twice that we're gonna do it for 1 year. So that's how we get the 2 right here. And after that, we get $2.25. Yay, a little bit better, right? Quarterly, as you can see, $2.44. Right? Monthly, so 12 times for the year, we're getting $2.61. Right? Daily, $2.71. Right? Hourly, even better. Oh my God, I never even seen hourly before. Once per minute, this is some Jeff Bezos type thing right here. All right. Once per second, yeah, I don't even know what that is. Like that's you wish. Right. Yeah.
They're making like 100,000.
Right? Exactly. Yo, the people on the bench make 6 figures in the NBA, man. The ones that they don't even shoot, like they go in if you up by like 50, like
You see what's his name?
Yeah.
He
Who?
got like 250 million for 3 years or something like that.
It's a blessing, man. It's a blessing. That's a blessing right there. All right, look. These values appear to be approaching a limit as n increases without bound. In fact, as n gets larger and larger, the expression 1 plus 1 over n raised to the n approaches a number used so frequently in mathematics that it has its own name, the letter E, right? This value is an irrational number, which means that its a decimal expansion goes on forever without repeating. Its approximation to 6 decimal places is shown. Let me show you that real quick. Yeah. This is what the calculator will give you. So the number E right here. Here you go. So the letter E represents the irrational number 1 plus 1 over n raised to the n as n increases without bounds, right? The letter E is used as a base for many real-world exponential models. The work with base E right? We use the approximation E is 2.71882, etc., right? The constant was named after a Swiss mathematician named Leonhard Euler, 1707 to 1783, rest in peace, who first investigated and discovered many of its properties, right? This is Euler's number. Yay. Euler, yeah. Some people say Euler, but I think it's Euler. All right. So let's look at continuous growth. Go ahead. Hmm? Yeah. 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 Not tomorrow, next week, Thursday. Yeah. All right. So investigating continuous growth. So far, we have worked a rational basis for exponential functions. For most real-world phenomena, however, E is used as the base for exponential functions. Exponential models that use E as the base are called continuous growth or decay models, all right? We see these models in finance, computer science, and most of the sciences such as physics, toxicology, and fluid dynamics. All right. Good stuff. Good stuff. All right. Let me show y'all what that is real quick before we wrap it up. So this is continuous growth and decay. This is the formula for it, right? So for all real numbers T and all positive numbers A and R, continuous growth or decay is represented by the formula A of T is equal to AE to the RT, right? Where A is your initial value, R is your continuous growth rate per time, and time is the elapsed time, right? If R, right, is greater than 0, the formula represents continuous growth. If R is less than 0, right, so negative, then the formula represents continuous decay, right? For business applications, the continuous growth formula is called the continuous compounding formula and takes the form A of T is equal to PE to the RT, where P is your principal or your initial investment, right? And R is the growth or the interest rate per time, and T is your period or term of your investment, right? Continuous growth. All right. Real quick, let me just give y'all a little bit of T, then we could call it at that.
So, like, yeah, graph, being the point where, but like the distance between, infinity and 0, kind of flat lines.
Not really.
Right, because like, at some point, I like drop from the ceiling, but I was going to the ceiling going this way.
Yeah.
And, you know, it's how you have.
E is your new base number. That's what it is. It's your base number for the exponential.
And that actually kind of seemed like it was like, okay, we're like so thin, but we're like increasing so much that we're like splitting hairs at this point. So this is the safe number that you should use once you get past.
Kind of, yeah. It's like a general number that we could all use. Go ahead.
Yeah. I understand, it just representative of overall radius within.
Yeah. Is representative like continuous compounding or continuous growth or continuous decay. Yeah. Right. It's just some number. Yeah. For decay, something that comes to mind. Have you guys ever seen styrofoam? Right? So that thing takes like forever to decay, right? So that's actually a an example of exponential decay. You know, like it just keeps half-lifing, huh?
It's not biodegradable.
I mean, it is. It will get broken down. Just don't expect it for like the next like eon or so, you know? Yeah. So that's an example of that. Real quick, let me just give you a little T. So given that the initial value, rate of growth or decay, and the time T, solve the continuous growth or decay function, right? This is how you do it. Step one, use the information in the problem to determine A, right? Your initial value, right? Of the function. Step two, use the information in the problem to determine the growth rate, R, right? If the problem refers to continuous growth, then R is greater than 0. If the problem refers to continuous decay, then R is less than 0. Step three, use information in the problem to determine the time T. And then step four, substitute the given information into the continuous growth formula and solve for the A of T. That's it. All right. Questions on this now?
Is there a name? These types of
Exponential functions. That's what we call these.
like E type people don't know, I type.
It's irrational numbers. Yeah, irrational numbers. Yeah. All right. So we good? All right, let's call it at that. I'm gonna stop the recording.
No, we're good. I mean, look, people that did the video with
Huh?
something out. And they say, yo, did you guys notice this?